All right, guys. Welcome, everyone. So now we'll carry on with our next lecture. So we were on multivariate Gaussians last time, right? So everybody understands what we mean when we say that the random vector is multivariate Gaussian. Uh, it just basically means that the joint density function is given has the following form. So this is V is a vector in R of D, and this mu is our D dimensional vector. Sigma is a is a matrix which is actually invertible, right? And then you can show with this joint density function that mu is actually the mean and sigma is actually the variance covariance of the components of this random vector. So we did this last time. Then we discussed bivariate Gaussian distribution. And the point you were trying to make was that when you assume that the random variables are uncorrelated, then the joint density function becomes a product of the density functions, and hence you have independence. So when the underlying distribution is bivariate Gaussian or multivariate Gaussian, then lack of correlation, uncorrelation implies independence. Not generally at all true, only true for Gaussian, for the most part. Camera's not on. Ah. All right, guys. All right, so we have that. And then we did an example of two random variables which were both, the marginals were Gaussian distributed, uh, and they were uncorrelated, but they were not independent. And that's because they were not bivariate Gaussian. So everybody with me on this, right? So you can see that their mass is basically lying on these lines. You know, if I give you a bivariate density function, that means the probability of lying in any area is just the integral of the joint density over the area. But this says that, okay, you don't have a joint density. So it's not bivariate Gaussian. Okay, let's move on then. So let's talk about multivariate Gaussian distribution again. So you're given this vector theta 1 to theta d. The characteristic function can be evaluated. I will not do this calculation. It requires change of variables. It's not that hard to do. But I'm evaluating this essentially, and the closed form solution turns out to be just like in the single dimension, it has a simple form. It's, as you can see, and I here is convex, is the complex value. So some big results, and let's talk about them for a moment. And help me with this. So V is a multivariate Gaussian random vector with mean mu and variance sigma if and only if for every theta in Rd, theta transpose V is univariate Gaussian. So can you appreciate this? That every linear combination of this multivariate vector is univariate Gaussian. And more importantly, the other way around, if every linear combination of a random vector is univariate Gaussian, then the random vector is multivariate Gaussian. So that's the other way to establish that something is multivariate Gaussian. So this is not just a statement, it has a proof, and my claim is that the proof is already given in this slide. So can you help me prove this? So let's go in one direction. So let's assume that theta transpose V is univariate Gaussian with this as mean and this as variance, right? Why does that imply that the vector, random vector V is multivariate Gaussian? Can anyone tell me? So just talk me through it. So what exactly should I be looking at? Of? So I've given the theta transpose V, it's a linear combination. I've given that it's Gaussian with certain mean and variance. So now what do I do?
So if you take the basis vectors as if it does, you know that you have like n linearly independent univariate Gaussians.
Uh-huh.
It's not saying it precisely, but and then those are the basis vectors. So if you that linear combination like that's a like sort of vector of n linearly independent univariate Gaussians.
Yeah.
This has to be multivariate Gaussian.
So let's not go all the way there. My point to you was that the proof is already in front of you. So can anybody take a crack and prove this?
I mean, so you have a characteristic function for the multivariate Gaussian on top.
Yeah.
Then you just like write it in terms of so theta transpose you just write it explicitly, and then you just take the expectation.
Right. See, I'll tell you what you do. Theta transpose V is univariate Gaussian, right? So we can evaluate its characteristic function. We know what the characteristic function of univariate Gaussian is. And that will look like this guy right here. Theta at a particular corresponding, let's call the alpha equal to 1, right? So that tells you that this term here looks like this guy. I mean, this term here looks like this guy here, right? Because theta transpose V is Gaussian, this quantity right here, because this is a Gaussian variable, right? This whole thing is a Gaussian variable. So I just take a univariate Gaussian and I know its characteristic function of a univariate Gaussian. I just plug that in here, I get this. So that tells me that for my vector, for this quantity right here, this characteristic function, the characteristic function is given as this for each and every theta. So now for my multivariate vector also, the characteristic function is given as follows for each and every theta. And that's exactly characteristic functions uniquely identify the distribution. So since this vector has the same characteristic function as a multivariate Gaussian, its joint density function must be multivariate Gaussian. So is this kind of clear? We know that this is univariate Gaussian, right? Hence, MGF of this and characteristic function of this must have the following form. Because for univariate Gaussian, there's I times the mean plus minus half times the variance. So this must be true. And this must be true for each and every theta. So the multivariate Gaussian V, its characteristic function is given as follows for every theta. Well, this is a definition, right? I mean, I've just shown you already that this guy here has the following form for every theta. So we've already shown it. And this guy here is actually the characteristic function of the multivariate Gaussian. The point is, it's a characteristic function of multivariate Gaussian at theta. It's also the exponential moment of random variable, this random variable right here, e to the power I, a Gaussian variable, right? Single Gaussian variable. So because it's for the single Gaussian variable, I get this form, and I get this form for every theta, then I conclude that my multivariate Gaussian characteristic function has the following form for every theta, and then I conclude that it must be multivariate Gaussian because it has the form of multivariate Gaussian. Other way around, if V is multivariate Gaussian, then this thing is true, right?
Yeah.
So same thing basically. That means that moment here, so I can put alpha times this guy. Let me do this way. I can plug in alpha times this, and I'll get, I guess alpha will come outside here. Yeah, I didn't think this through. Yeah, well, I mean, what's the moment function of a single dimension guy? It's I times, so I want to evaluate e to the power alpha x. X is Gaussian distributed. This should be e times I times alpha mu minus alpha square, sigma square by 2, right? So if I just multiply all the thetas by alpha, I'll get alpha here and I'll get alpha square here. Because I know that this is true. I know I have a multivariate distribution, so I know this is true for every theta. So it's also true for theta when I multiply it by alpha. So I get the following expression, and this is nothing but the characteristic function of this combination of this random variable, right? So this random variable must be univariate Gaussian. I mean, this is a characteristic function of this random variable, and it has a form of univariate Gaussian with the this as the mean and this as the variance. Yeah. So I get the result in the other direction. Is this kind of clear? That if I told you this is multivariate Gaussian, then I go ahead and ask myself, okay, what's the characteristic function of theta transpose mu, right? That's what I'm asking. What's the characteristic function of theta transpose? Sorry, I'm just going berserk. What's the characteristic function of theta transpose V? Okay. Now I can evaluate the characteristic function of theta transpose V, because all I'm trying to do is I'm trying to find e to power I alpha this guy. And because I have this formula here, I can evaluate this. So I get an evaluation of this guy, and that turns out to be characteristic function of univariate Gaussian. And univariate, characteristic functions uniquely identify a distribution. So my distribution of this linear combination must be univariate Gaussian with the corresponding mean and variance. So you're with me on this, right? So we assume multivariate Gaussian, we got univariate Gaussian. We assume univariate Gaussian, we got multivariate Gaussian. All right. Okay, let's go a little further. The next quantity right here. Suppose our V is multivariate Gaussian mu and sigma. Then if I multiply this random vector V with the matrix A, so I'm just taking linear combination of V's. So these are not linear combination of bases, they're just linear combination of V's themselves. And the claim is I still remain in a multivariate Gaussian family. So linear combinations of multivariate Gaussian gives me another multivariate Gaussian distribution. Is this a? Yeah, yeah. No, that's a fair comment. But yeah, how do we prove this? It does require a proof, right? So if I'm saying A times V is a multivariate Gaussian, then A times V will have a characteristic function. And then using the same univariate kind of logical match. Sorry, so you're saying decompose A times V. Think of A times V as a vector, basically. Yeah, okay. Uh, Actually, that will give me a univariate guy. And I mean, it's each one will be univariate, but I want to show that, okay, if each one of them is univariate, then you're using the above result, basically. Sure, sure. More, I mean, it's essentially the same thing, but more direct way is that you.
So how about the radical e raised to the power I alpha theta transpose times AB?
Yeah, exactly. That's exactly what you should do.
And then you expand on it.
Right. What you want to do is, let's call exactly what he's saying, what Aman is saying, let's call y equal to AV. And now we want to show that E of I theta transpose Y
That matches
has the characteristic function. Yeah,
VG.
that's right.
Multivariate version of this.
That's right. Exactly right. So what that means is we'll get now A times V here, right? And essentially now we have a different theta, right? It's e to power I gamma V, where gamma is equal to theta transpose A. Okay. So we have to evaluate this guy, and we should be able to say that it's
I gamma transpose V.
so does anybody want to help me?
Yeah, e raised to the power minus, sorry, e raised to the power I gamma transpose mu minus half gamma transpose sigma gamma.
I mean, that's what we want to show. Um, but your point is theta transpose A we are taking as gamma right now, right?
Yeah.
Right. So right. Actually, let's call it, shall we call it gamma transpose? Okay, so the point is I'm hoping somebody is going to jump in.
Can you reiterate what exactly you're trying? I'm a bit confused.
Well, we are trying to we've come up with this. Yeah, this should be. Let's write it down. What we want to show is E of I raised to power gamma transpose V. No, Y. Y. Right? Is equal to E to the power I gamma transpose mean of Y. What's the mean of Y? What's the expected value of Y? A times mu, right? And what's the variance of Y? What's the sigma of Y? Hmm?
A,
A square times sigma.
Right, variance covariance. So this you can think about this, but it's going to be A sigma A transpose. Right? So you want to show that this is, let's call this A mu, and then you have minus half, and then you have gamma transpose A sigma A transpose.
And then gamma in the
Gamma in the end as well. What do you mean?
so like half gamma transpose A
Oh yeah,
sigma A
that's right.
transpose.
That's right. Yeah,
Gamma.
yeah, sure, absolutely. Right. Yeah. So how do we show this? We have this, right? I guess we can just take theta transpose to be gamma transpose A, right? Right. Then this follows. Do you see it? We just go here. Wherever we have theta transpose, we substitute it by gamma transpose A. Right? So here also we'll have theta transpose is gamma transpose A, and this is A times gamma. So we get this expression. Okay. So hence this follows. So is this clear? For every gamma we get this.
so where does the A transpose next to the V? I mean, so can you repeat what gamma, the gamma is defined?
But initially we defined theta equals to gamma transpose A.
Right.
Now we're saying, okay, so we define theta transpose equals to gamma transpose.
That's right. We we want to show this quantity.
Hmm.
We want to show this, right?
Hmm.
Then we'll be done. We have this. Now we just substitute, we just take theta transpose to be equal to gamma transpose A. So, Siddharth, is that okay? Yeah.
But how are we first defining gamma as like initially?
Well, gamma is defined through this equation. Right.
Wait, I'm still trying to understand. Gamma should be theta sorry, gamma should be theta transpose A.
So gamma here, so what does this mean? This means theta is equal to A transpose gamma, right? Right. Yeah, you should take a gamma, look at A transpose gamma, plug that in here. You can always do that.
Yeah.
And you get this.
Okay.
That's
Check.
it. That's it. Yeah. It's not, nothing has to be inverted.
Hmm.
You start with a gamma, define your theta to be A transpose gamma, plug that in this equation, and you get the following relationship. And this is what you need to prove that
It's a
Y is a
multivariate.
multivariate Gaussian with the right mean and right variance. So is this kind of clear? We just want to show that y is multivariate Gaussian. So we know exactly what the characteristic function of y should be, because we know the mean of y, we know the variance coefficient of y. We need to show this. We have this guy here. So now we simply plug in the right theta and we get our result. All right. Okay, good. Ready for a question in the quiz? Okay, now we'll formally define independence. We've assumed independence. Yeah, go ahead. The space of because every linear combination of univariate Gaussians. Yeah, that's true. Mm.
Extend that same sort of until last 2004.
So let me try to understand your point. So I give you a bunch of univariate Gaussian. I mean, the point is multivariate Gaussian is not kind of a linear combination of univariate Gaussians, right? The linear combination of univariate Gaussian is again a univariate Gaussian term.
So I guess if you look at a univariate Gaussian as a degenerate multivariate Gaussian in like n dimensions, then the multivariate will be a linear combination.
That makes sense.
What is degenerate?
Meaning it's kind of it's zero on all the other dimensions. It just has one. I mean, as such, of course, one doesn't define multivariate Gaussian to be degenerate. You know, multivariate Gaussian means that you have a full density variance covariance matrix is invertible. But so yeah, maybe something can be said, but it sounds like it needs some more refinement.
But we are avoiding saying that multivariate Gaussian is a vector of univariate Gaussian. And it's true that a vector of univariate Gaussian is multivariate Gaussian, but if you look at all the definitions and all the results we're trying to show,
Yeah,
we are explicitly avoiding making this statement. Right? Because I think
it's not an easy statement to make, right? You can't really say that it's a linear combination of univariate,
a vector of univariate Gaussians.
a vector of univariate Gaussians.
We are avoiding that statement. Right? It's according to your side.
I mean, certainly this statement is there that if I give you a multivariate Gaussian, then each component is a univariate Gaussian. And linear combination of these guys is a univariate Gaussian. It is also multivariate Gaussian. That we are saying. I think her point is somehow she wants to view each multivariate Gaussian as let's collect the space of all the multivariate Gaussian variables, right? And you want to kind of say that, okay, it's n points of that space. These are all linear combinations of kind of what you were saying, univariate Gaussian. Let me hold on that one. Huh? Yeah, it seems that one needs to be careful in pushing this. All right. So we've been using independence throughout, but again, everything gets reinterpreted in this more general setting that we're playing in now, right? We have a general space, general sigma algebra, general random variables, more general than we are used to. So we have to define independence also in this generality. So it turns out that, the right definition for X and Y to be independent is that probability of A intersection B is probability of A times probability of B for all A in sigma algebra of X and all B in sigma algebra of Y. Right, so that's how we say two random variables are independent. Essentially, we are saying that two sigma algebras are independent. Sigma X is independent of sigma Y.
P A intersection B is now the product.
Yeah,
It's from the product space. Like,
it's
you take two of these independent guys, look at the product space and the product measure.
no product space. A intersection B, it's just Venn diagram.
No, but yeah.
It's on the same space. I mean,
No, but sigma X and sigma Y can be distinct guys, right?
sure, sigma X and sigma Y can be distinct.
That's the measure.
Right. Right. So your point is, I mean, we can look at the sigma algebra which corresponds to the product of, which makes X and Y jointly measurable. Yeah.
Yeah, so my question is then X and Y need to become the same measure.
Yeah. Yeah, of course. I mean, for this to make sense. So there's an underlying space omega, there's a sigma algebra F, and there's a probability measure P, same measure, on which we define random variables X and Y for us to say all this. So there is independence is very much a function of the probability measure. On the same space, a different probability measure, I won't have independence. I need not have independence. But yeah, this should be defined that there's an underlying space here. And right. So sigma x is a sub-sigma algebra of F. Sigma y is also a sub-sigma algebra of F. Sigma of x and y is also a sub-sigma algebra of F. Okay, and this you can show, and we will not show this here, that independence means, and this is important to know, that expected value of g of x times h of y breaks out in the product of expectations for any g and h which are Borel measurable. Right? So this is if and only if. One direction is straightforward. Can you see that? Can you see which direction is straightforward?
Left to right, I mean. They're
Well,
independent,
so you mean up to down, is that what you mean?
Yeah, up to down.
Up to down, okay.
And that's just because if you look at expectation definition so far, you can then just separate them.
I mean, up is just probabilities, right? It's a statement about probabilities.
Yeah, no, but if you look at the definition of how we have defined expectations,
Yeah.
then you can just replace f x a union b with a b and then separate the total length of them.
So you have to construct, you have to do all of this, here. You're right, you can separate the probabilities. That's true. So x lying in some set, y lying in some set, we can write a product.
And you can,
You have to come all the way till here.
no, so up to down, down to up.
That's why I'm playing with you, that it's not up to down, it requires a lot of work.
Up to down requires a lot of work.
Yeah. G and H are general Borel measurable functions. So in split, you're right, you'll say, okay, let's take G and H first to be indicator functions of some sets. And so it follows from here. Then argue that G and H are simple functions and argue that this works for simple functions. Then for non-negative function, approximate them from simple functions, take the limit. So that's how you'll go. So it requires a bit of work to make everything work. On the other hand, the other way around. So this direction is straightforward because I can always take G of x to be just indicator that x is in A. And H of y is just indicator that y is in B. And then this from here, this follows immediately. So is this clear? All right.
But would it be sufficient if we're just like taking some instantiation of gx?
Hmm.
So we're taking an indicator function. What about if it's a general function?
You're saying that, well, I mean, we've already, in some sense, this is an instantiation, right? This is saying this the indicator functions are enough to show independence. So these two are equivalent. So just look at G, which are indicator function of x lying in any Borel set. H is indicator of y lying in any Borel set. And if you can show this, and if you can show this for those indicator functions, then you're done. Which exactly is this property right here. Right? That's your point, right? You're saying, is there a subclass of G and H which does the job? So I'm saying, yeah, just indicators will do it. And you can construct other subclasses, but it's not interesting. All right. So now let fxy be joint density of x and y, right? So then x and y lying in some Borel set in 2 dimensions is given by integral of the joint density over that two-dimensional set. Right? Marginal is defined as follows. That we know from elementary probability, so I'll just go with that. And similarly, fyy, right? So then we've already used this fact that x and y are independent if and only if, and I'll do this calculation for you. Joint density function is product of the marginal density functions. Both directions. If this is true, that implies independence. If you have independence, you apply this. So we need to show this. So essentially, we need to show this property, right? So we'll first assume x and y are independent, so we'll assume this. So this is assumed now. And what we really assumed is this quantity right here. Right, when x and y have a joint density function, then this probability is exactly given by this expression. This probability is given by this expression. This probability is given by this expression. So we have this already for all A and B, all Borel sets A and B. We can take our Borel sets to be minus infinity to U and minus infinity to V, right? So even then we have this quantity right here. What we want to show is this term, this equality, the product form. So how do we go from here? How do we show that this implies this? Should not be that hard, right?
You can represent that integral on the right hand side as the sort of maybe a cumulative distribution function of x. So
Right.
f x less than equal to u basically.
Yeah.
And that you can do similarly for y. So then you've shown that like x comma y, x being less than equal to u, y being less than equal to v is equal to the product of
Yeah.
the integrals. And then because you can generate the Borel like sigma algebra with these kinds of intervals just by taking intersections.
But mind you, where we have to go? We have to show that the joint density is the product of the marginal densities. Maybe something easier. You can just differentiate both sides with respect to u and v, right? When I differentiate, right? And then I'll get this quantity right here for every u and v. Okay. That's all. We just take the derivatives on both sides. We get this quantity. Okay, for other direction, it's much simpler. You have this quantity is given to you, and now you integrate it, right? And apply Fubini's. So Fubini's tells you basically that the joint integral can be written as marginal. You can iteratively solve the marginal integrals, and you get this term here. All right. Okay, finally we come to conditional expectations. So now we start talking about conditional expectations. So you all have, you've done your conditional expectations, right? You're conditioning on an event that changes the probabilities, and now you find expectation with respect to change probabilities. That's what conditional expectation is. So let's take an example in discrete settings. So x is a random variable which takes values in this calligraphic x space, discretely many. Y takes values in this calligraphic y space, discretely many. Probability that x is equal to small xi given y is equal to small yj is given by this formula right here, basic probability. All you require is that the denominator should be positive. If the denominator is 0, the numerator is 0, it doesn't matter. You can call this conditional probability 0, makes no difference. You're just conditioning on a 0 probability event. At least in elementary probability, that's how we do things. Okay, and then the conditional expectations given as follows, just expectations with respect to new probabilities, right? This quantity right here, which is exactly this quantity right here. See, the point is this. We are asking ourselves how to extend this idea to general random variables and how to do conditioning with respect to general random variables, which are not discrete, where the probability of where the denominator is often 0. How do we do these things? How do I define this quantity when the denominator is 0? As let's say in the continuous variables, right? So in continuous variables, you've seen the formula with joint density functions and conditional density functions. We'll come to that later. But the bigger problem remains because we are going beyond continuous variables and beyond discrete variables. Okay. So let's, so we can partition omega into these m sets, y1 through ym. right? That's all the possible values of random variable y takes. We define z omega to be e of x given y equal to yj if y omega is equal to yj. So we define a new random variable z of omega on the whole space. On every omega it has value. And then z, this random variable is just e of x given y, right? Now e of x given y is a function of y. Earlier it was like we fix y equal to yj and we get a positive number, but really we are getting a function of y. So it's a random variable itself. So conditional expectation is a random variable, right? That's the idea we want to carry with us. And it's simpler when you're conditioning on a random variable.
Professor, shouldn't it be y omega belongs to yj instead of y omega? Because why are you defining them as sets itself?
No, we look at all the, see, all our, this is our safe space, right? These are all the omegas where your y is equal to y1.
Oh,
This is all the omegas where y is equal to y2.
Sure.
So we go to all the omegas where y is equal to yj. On that we call z equal to this quantity right here. It's a constant over there. It's just a function of y. So once I fix a y, I get a constant value, right? So this property we know already of our conditional expectation. So in particular, now you can see from this expression right here, because I want to get away from dividing by something which goes to 0. I'm okay multiplying by things which where the product is 0. That's perfectly, that's a well-defined operation. So I'll just take this quantity on this side right here, right? So I get probability y equal to yj into this conditional expectation, right? And now I can sum over all yj lying in A. I mean, this product here is just this summation for yj fixed. So all I've done is I've summed up both sides over yj belonging to some set A. So are you with me so far that this equality is true?
on the top side. So we're somehow moving the probability that y equals to yj to the.
That's right.
versus-
We moved it on this
Sorry,
side. Yeah. We moved it here. And then we said, okay, even y equal to yj is a 0 probability event often. So we don't want to talk about these. So, let's just talk about summation of these. The summations will become integral. Those things make sense when the individual events are 0 probability events. So that's what we did right now. We just put, we brought this here. We brought this quantity here, and then we summed over yj, both sides. And we get the following equation.
So script X and script Y are just the sigma that was of X and
Yeah, the script X and script Y right now are just these spaces.
is there the. So this is magnetic point, then A is not belonging to script Y, right? A is a subset of script.
Yeah, now.
Yeah. Yeah, A is a skip set, is a subset of skip Y.
So we're considering a fixed set by J, now we're looking at a set of these.
Yeah, that's all we've done. And the point is, these sets we can extend to integrals from summations. It's a meaningful thing to do. Right? So now really what we've done is we've done this quantity, just to generalize it so that we can state things generally. We're saying E of x given y integrated with respect to probability measure P on the set A is integral of x dp on the set A. Set A is y lying in some set, but set A is y lying in subset and x lying everywhere. Same thing.
I don't see what does this tell us?
I mean, right now we're just saying that this is also true. That this equation here is exactly this equation. That's all I'm saying. Right? I mean, the nice thing is that the below equation is generalizable. So it's true for elementary probability, but it extends more generally.
Is that this we just get by taking limits?
Well, I mean, right now I'm just, there's no limiting here. I'm just saying that this integral here in the discrete setting is exactly this value here, And this integral is exactly this. There's no limiting operation here.
Yeah, that I get, but down to a.
No, I mean, I'm giving you right now, we're just talking about discrete variables. So there's no approximating and taking a limit. This is just a more confusing and fancy way of writing this quantity right here. So you have to keep in mind this integral xdp, when the random variables x are simple, is just summation of all the values the random variable takes, weighed by the probability that it takes those values. Yeah. So this is exactly this quantity. Right. But this is a random variable which takes finitely many values.
What's the expectation of x given y?
So
I mean, right now I'm integrating over the set A. Yeah.
if A was part of X, then it would have, if A was all of X.
Of course, yeah.
Then it will be X.
This is just Tower property.
And this is just x being integrated over this set A.
This is just Tower property, now if you look at it.
This is the
Tower property. Expectation of X given by.
No, but that expectation X of expectation.
Let's define conditional expectations before we start doing tower property.
What is inside the sums, normal sums, the discrete sums, the measures are not the same. One is a joint distribution, the other is,
Yeah, that's true.
yes, how did you like?
Yeah, one is a probability measure defined on the sigma algebra of Y. One is the same probability measure defined on a bigger sigma algebra. Right? Sigma X cross sigma Y. That's true.
I don't see how.
Hmm.
it to the last time.
In the sense that, this probability measure is defined on a bigger sigma algebra. So it's still the same probability measure. It's defined on sigma X as well as sigma X cross Y.
Okay.
So you can do these things. Okay? So this tells us how to generalize and define conditional expectation in a more general setting. All this hard work we are doing was we're generalizing everything to, like for example, Riemann integral was simple, but Lebesgue integral required, we have many more things that for which this integral exists. So we have much more general random variables for which we are defining properties. Okay, so conditional expectation of random variable x defined on the space omega fp. And just to make our life as simple, we'll assume our x is integrable, so we don't have to worry about infinity minus infinity situations. So now we're taking conditional expectation with respect to sigma algebra G. So sigma algebra need not correspond to just random vectors, random variables. They can just, as long as they satisfy properties of sigma algebra, it's a sigma algebra. So we're now defining conditional expectation not with respect to random variables, but with respect to sigma algebra. But intuitively, just think of always, whenever you condition on G, think of G as just sigma algebra corresponding to random variables. So then we are defining conditional expectation given those random variables. So that's a pretty good way to think about this to begin. So it's defined as follows. So we've come up with a new idea now, which is conditional expectation not with respect to a random variable, but with respect to some sigma algebra G. Typically, G will be smaller than the sigma algebra that X is measurable with respect to. So you have less, and the idea you're capturing is, conditional expectation is kind of given Y is equal to small y, what's my best guess for X? It's a conditional expectation. So I don't know X, I have some partial information that Y is equal to Y, I. What's my kind of smoothened version of X? That's E of X given Y. It's my best guess given I have limited information. So that idea will continue. Yeah.
It's not a control, but the intuition behind what you're saying is that if the sigma algebra G was bigger than sigma X, the conditioning won't give you any more info.
That's right. Then you'll know X. We'll just talk about this in a moment, but that's exactly right. But it really is kind of, I know the sigma algebra G. And what I really mean is, if you give me, there's an output, in a random experiment, there's omega that has happened. I don't know that omega, but I know whether it belongs to each and every set of G or not. Sigma algebra G. So I have information of G with me. What's my best guess of X given this information of G? So that's a way to kind of think about this. So for any omega, I know which set in G contains it. Now given this omega, what's my best guess for X? So E of x given G is going to be a random variable which is G measurable, right? So it's like E of x given Y is sigma Y measurable, right? It's a function of Y. So more generally, it's G measurable. And second property is on every set G in calligraphic sigma algebra G, it integrates like X. So that's the definition of conditional expectation. Huh? It's a very kind of non-trivial definition. Now, it's not something that immediately strikes you, and it's hard to grapple with. So whenever I talk about conditional expectation, I mean something which satisfies both of these properties. So E of x given G is G measurable, and it integrates like X. It's a smoother version of X, but it represents X on the sets in calligraphic G. It integrates like X. Yeah?
So is the valid defined like is it really weak? Is there
Yeah.
one that-
Yeah, so we'll discuss all that in a moment. So that's a great point. It's actually it's always defined. So for that, we'll use Veda-Nikodym theorem. It's a big theorem, but we won't prove it. We'll just use it. It just follows immediately from there. We'll also define it through L2 geometry. So two different ways we'll define this. And we'll also argue that it's unique. Okay? But this is an idea that you just have to kind of see often enough that you get comfortable with it. It's not something that naturally comes.
We define what the ultimately expectation.
E of x given G. Yeah, this condition expected.
Projection.
That's right, yeah. Okay, so you're with me on this definition, right? And now you can see that if indeed x was G measurable, so I'm going to write it in this following fashion. This means x is G measurable. Mg is all the random variables with a measurable respect to G. X belongs to that class. Then what do you think? What is E of x G given G? Can you think of an answer for this?
So G of x G.
Suppose x is G measurable. Then what is a conditional expectation of x given G?
Just expectation.
Expectation.
Just expectation of x. Just expectation of
Why?
x.
Because you have all the information.
Right, right, right.
You don't have any information.
Yeah, you're conditioning on the fact that G takes all.
So you have all the information you need about x and G. That's what I'm saying.
You don't have any more information.
You have all the information.
Huh.
So that's what. That's fortunate. Exactly. Everything is in.
Very.
If you wanted to integrate like it should be X, right? But
It's x, yeah, yeah. It's very. I was trying to see where I can show what you're saying is wrong, but
It'll be X.
it'll be x because then x will be G. It has to satisfy these two conditions, right? So x is G measurable because we've said x is G measurable, and x integrates like x on the sets of G. So x will certainly satisfy these conditions.
X. Okay, I see.
That's just by the second call.
Yeah. So I mean, I know if I know all the information, by knowing G, I know x because x is G measurable. So then my best guess of x given G is just x itself.
Oh, yeah, it is a random variable.
It's a random variable. Yeah. ठीक है?
Should be expecting.
No, it will be exactly x. So in that case, so E of x given G is equal to x when x is G measurable. Right? So it's a random variable. All right, so this is fine. So you've got these 2 points, right? Just remember them. See them again and again. So E of xg exists and is unique. So these are addressing Siddharth's questions. So suppose, yeah, but this quantity is, for this, 2 variables can satisfy this property when they're equal almost surely, right? And the 2 variables can be G measurable almost surely. I mean, both of them can be G measurable. So what I'm saying is that we are really defining this conditional expectation, up to the almost sure equivalence.
We're just saying that expectation
So the left hand side and the right hand side are equal, almost short. That's what we say.
Yeah, let me just put it this way. This, I think I jumped the gun a bit. Suppose y1 and y2 are two random variables which satisfies the property of E of x given g. I've given you the property that E of x given g should satisfy. Suppose y1 and y2 both do the job. Then y1 is equal to y2 almost surely. Is this part clear? So they're unique in this sense that they're equal almost surely on a set of probability 1. They're not equal everywhere.
Oh, and as it is the-
So that's what we'll show right now. But in that sense, conditional expectation is defined up to this almost sure equivalence. And by the way, let me just emphasize here, I didn't do that enough, that this is true for every G set in calligraphic G. So it's a big property that we are asking. It has to integrate like X on every set G. Which is what we saw here, right? This would have been true for every set A. In elementary probability, we do get this for every set A. All right. So how do we show this? What do we have? We have that y1 integrates like X on sets in calligraphic G, and so does y2. Right? That's given to us because y1 and y2 are both candidates. And this implies that integral of y1 minus y2 dp is equal to 0 for all G in my sigma algebra, calligraphic G. Everybody with us so far? I want to now argue that this means that y1 and y2 must be equal. Right? Now I know y1 and y2 are measurable. G measurable. Again, there are two candidates. They're given to be G measurable. Then one can argue that y1 minus y2, y1 plus y2, y1 times y2, y1 divided by y2, all of these are measurable functions. You'll prove some of that in your homework right now. Okay, so the y1 minus y2 is also G measurable. That means that this set, omega where y1 is bigger than y2, that's also in my sigma algebra G. Right? So even this property is true. Okay? So this guy on this set is positive, but the integral is 0. Right? So the set must have probability 0. That's what you expect to be true. So that means the set where y1 minus y2 is less than or equal to 0 has probability 1. And set G is probability 0. Set G complement is 1. Symmetrically, y1 minus y2 greater than or equal to 0, 0. So hence y1 is equal to y2 almost surely.
Wait. Probability that y1 minus y2 will be 1.
Yeah, because probability of G, this G here
And
is
we
0.
got a similar argument. You already know that the
Right.
integration over G of S is 0.
So, what I'm saying is if I tell you that a positive random variable is integral on some set G is 0, then the probability of the set G must be 0. It can't be that the G has positive probability and the random variable which is positive on it, then the integral will be positive. Yeah. So,
But the second statement.
so then G has probability 0. This is just G complement. y1 minus y2 greater than 0, its complement is y1 minus y2 is less than or equal to 0. That has probability 1. Similarly, y1 minus y2 greater than or equal to 0 has probability 1. So the intersection of two sets also has probability 1. And that's y1 equal to y2, almost surely. Okay. I'll just, drill down a little bit on this, my earlier comment. So what I claimed was that probability of x dp equal to 0 on the set x greater than or equal to 0 implies that probability of x greater than 0 must be 0. That's what we used right now, right? We then, if this is 0, we said that this implies that this probability must be 0. Right?
just clarify something rotation wise. When you say integral over x greater than equal to 0, you're using integral over the sets where x is.
All the omegas such that x omega is greater than equal to 0. Yeah, when we talk about random variables, because notational clutter gets a big pain, so we hide omega. It should be understood. Okay, so just to see this more cleanly, suppose this is not true. You realize that this is exactly the set where probability of x is greater than 1 by m union over m. If x is greater than 0, it's greater than 1 by m for some m, right? If x belongs to this set here, then x is greater than 1 by m for some m, then x is greater than 0. So we're talking about the same sets. Okay. So this is important because we want to break things down to countable operations that we know how to play with. Yeah?
Uh, when you're talking about existence of conditional expectation, why do we suddenly need x like integration of x integrated to the 0?
No, I just kind of use that here, right? I use this fact that this being 0 implied that P of G was 0.
Yeah.
So I just want to show that.
Oh, I see.
Okay. So I'm saying that this quantity right here is 0, implies that probability that x is greater than 0 must be 0. But the point is this set is same as this set. And for this set to be positive, at least one of these elements must be positive. One of these constituent sets must be positive. So there exists some m so that probability of x greater than 1 by m is greater than 0. That must be true. Because all of these are 0, then the union is also 0. Okay? So then that tells me that this integral here is dominated from below by 1 by m into probability x greater than 1 by m. And that gives me a contradiction. Right? Because this quantity here is positive, while this integral here is 0. So my premise that this quantity was sorry. So my premise that this guy was positive was wrong. This probability must be 0. Okay? So this argument is useful to see because otherwise we kind of say things without really being completely clear about them. This is a more rigorous way of saying things. This is the right way of saying things. Okay? Okay, so what have we achieved? We just argued now that if there are two versions, then they must be equal almost surely. Right? But we've not argued that there exists a version. That needs to be shown. So we'll show this in the using the Radon-Nikodym theorem. It sounds like a powerful theorem and it has applications which are powerful, but it's actually quite a straightforward thing if you at least start simply. So I give you this space omega f. First, I'll define the notion of nu being absolutely continuous with respect to mu. So measure nu is absolutely continuous with respect to measure mu. So that's a definition I need. What does that mean? That means if mu a is equal to 0, then nu a must be 0. And if nu a is positive, then mu a must be positive. So mu has a support where it puts positive mass. Nu's support is a subset of that. Nu is not putting positive mass somewhere else where mu is putting 0 mass. Right? So if mu a is positive, it's not like mu a is 0. Mu a must be positive. So you must be on the support of mu in that case. And if mu a is 0 somewhere, then mu a must be 0. These are just equivalent statements. So is this clear what we mean by nu being absolutely continuous with respect to mu? So advantage, and it's easy to see this in discrete setting. So let's assume omega f is a discrete space, right? Then what I just showed you here, that nu a being positive implies mu is positive. What this really boils down to is that whenever mu of omega is positive, implies nu of omega is No, the other way around. Whenever nu of omega is greater than 0, implies mu of omega is greater than 0. And whenever mu of omega is 0, nu of omega had better be 0. That's what absolutely continuity means of nu by mu. And what that really means is that this ratio is well defined. When mu of omega is 0, nu omega is also 0. We just think of this as, doesn't really matter what we think of it. It's a probability 0 event. You can think of it as 0. And whenever nu of omega is positive, mu omega is also positive. So we're not dividing by 0. So we're dealing with positive quantities. So that's really what we are trying to capture in generality, that this ratio should be well defined. And what this Radon-Nikodym theorem says is that whenever nu is absolutely continuous with respect to mu, there's a density function f, so that nu of a is equal to integral of a f d mu. So there's a random variable density function f, so that nu of a is equal to integral of f d mu. Okay, that's what it's saying. But it's not really a big deal, right, in a discrete setting. All we are saying here is that we can write nu of a as summation f omega mu omega. We can do that because f omega is just nu omega by mu omega. We're just dividing by mu omega and multiplying by mu of omega. Yeah?
You can go ahead.
Huh.
So, I just want to ask if, so this thing is well defined because of this absolute probability, but if they're both 0, then why is that well defined?
Then it doesn't matter, it's happening on a set of probability 0. So in the almost setting, it doesn't matter. You can define it to be whatever you want. You can define it to be 0, for example. Any value you give it won't affect the calculations.
So the point is that if the set was non-zero, there is some measure we want the.
Yeah. So in the discrete setting, yeah, we don't want to divide by 0. Right? Otherwise, this is, what is this quantity right here? It's just summation nu omega, right? Omega is in A. And now we divide by mu omega because we can, and multiply by mu omega. And we define the ratio nu omega by mu omega. It's called the likelihood ratio as the density function. So likelihood ratio is really a density function between two measures.
That's why it's called Radon-Nikodym derivative.
It's called Radon-Nikodym derivative for that reason. That's reason, yeah. So this is, it's such a nice and simple fact. But if I didn't mention this discrete example to you, it would appear mysterious. The result is, so this is a Radon-Nikodym theorem, extends this to general spaces. If nu is absolutely continuous with respect to mu, then there exists a density function f. It's basically a random variable, which is f measurable. It's a random variable, such that nu of a is integral of f d mu for a. And random variable f is known as Radon-Nikodym derivative and denoted as d nu by d mu omega, the likelihood ratio. Okay. So it's a slightly non-trivial result now, right? Because it's in generality. So whenever nu a is absolutely continuous with respect to mu a, it has this representation.
And this F is also unique.
Yeah.
Almost only with the same argument.
Same argument as we gave before, yeah. Exactly the same argument that we gave before. Because if we have F1 and F2, then F1 must be equal to F2 almost surely. Okay. So now you have this, right? I'm not going to prove this result. You kind of know what we are trying to do here. In discrete setting, it's very clear, but it takes a lot of work to extend this. It's not such a simple. Well, some proofs of this are quite demanding. Under some mild assumptions, you can get nicer proofs, but let me ignore that for now. Okay, now we come to our problem. We want to define conditional expectation. We want to say that the conditional expectation exists. And let's just do this for any random variable x. Let's do it for non-negative random variable. For general random variables, we'll think of them as difference of two non-negative variables, and we'll be able to kind of extend the argument. So for now, assume that x is non-negative, integral of x dp. Okay. I'm going a little fast in the sense that it's very crowded in my slides here, but you see this definition. nu g is equal to integral of x dp over g. It's not that big an argument to show that nu g that I've defined, in this manner is actually it's actually a measure. It satisfies the properties of a measure. Measure meaning um, it's a probability measure if the total measure is 1, but if total measure is not 1, then it's a general measure. Countable additivity still has to hold, non-negativity still has to hold. Okay? But Radon-Nikodym theorem is about two measures, nu and mu. And when we defined the Radon-Nikodym theorem, we didn't assume that nu and mu were probability measures. We allowed them to be general. So these are points which I've kind of not spelled out enough in my notes, but I hope they're clear. Okay. So now the other point is that whenever Pg is equal to 0, implies nu g is equal to 0. Right? Because I'm integrating over set of measures 0, the integral will be 0.
But we don't know. Pg greater than 0 implies nullity.
That may not be true.
But we needed that for the definition of absolute P.
No. What we just need is Pg equal to 0 implies nu g equal to 0 because
Because we're dividing.
the reverse is true, right? If Pg equal to 0 implies nu g equal to 0, then nu g being positive implies Pg must be positive. If A implies B, then B complement implies A complement.
No, that I understand. But that doesn't tell us that Pg not being 0 implies Vg not being 0. We know Vg not being 0 implies Pg.
No, but that's okay. But we don't need that. We just want nu g. If nu g is positive, then Pg must be positive.
Oh, because we're dividing with Pg. So
that's it. That's all we need. Yeah. So you're with me on this so far, right? So I've defined a new measure, and I've argued that if I define a measure like this, it must be absolutely continuous with respect to the measure P. Okay? So now Radon-Nikodym theorem tells me that this must have a density with respect to P. The point is this. This point needs to be emphasized. I've defined this measure for all G in the sigma algebra G, calligraphy G. So on this sigma algebra, measure P is defined, the new measure nu is defined, the new measure nu is absolutely continuous with respect to P. So this measure nu will have a density with respect to P on this sigma algebra. What does that mean? That means there exists a G measurable random variable Y such that nu G is equal to Y dp. How confused is everybody? Huh.
I mean, all you're then saying is that you take another measure and then just take F by that measure and you get parameters.
So this Y, that's it. So this Y is, so let me just complete the story, then I'll come back to it. I see what you're saying, but I see some people are lost. But the point is this. Oh, yeah, I just stopped there. But the point is this Y is equal to E of X given G. So you see, it's a kind of a clever argument. I define this measure as follows. I could have defined this in all of F, sigma algebra, but I restrict myself to sub-sigma algebra, calligraphic G. So I define this measure here, and now I argue that P and nu is absolutely continuous with respect to P. Because whenever P of A is 0, nu of A is 0. So they satisfy the condition of our Radon-Nikodym theorem, and hence there exists a Y such that nu G is equal to Y dp.
But how does this follow from the radon theorem?
Well, Radon-Nikodym theorem just says that whenever nu is absolutely continuous with respect to P, on a sigma algebra, it has a representation. It's an integral of some Y times dp.
Yes.
That's what this was, right? That's what Radon-Nikodym theorem was.
Please. You just take a step back.
Yeah.
You know that integral of gx dp will be equal to expectation of x. No, not expectation. Integral of expectation of x over g. Wait. I mean, don't we have to from the definition that if you take the integral over g of expectation of x given small g. No, no, I read the data.
So let's just go back. What do we know? So what do we have?
In your
Huh. What are we trying to show, first of all? Let's just be very clear. I'm trying to tell you that there's a random variable, which is g measurable, ex given g. This random variable exists. So when I integrate it over small sets g, it integrates like x dp for all g. I want to show you that such a random variable exists. It's g measurable. I want to show you that. We don't know that right now. Of f. That's right. I want to give you this random variable. We don't have this right now. This has to exist. What I have is a random variable x, which is defined on a bigger sigma algebra f. What I do is I construct this quantity right here. And I define this for all sets G in my sigma algebra calligraphic G. I can do this. Okay? XDP is, it's x times I of G is a well-defined random variable. It has an integral. That's what this integral here is. So now I've defined nu G on sigma algebra calligraphic G, where nu now is absolutely continuous with respect to P. So because it's absolutely continuous, it has this representation here. So now what do I get? I get y dp is equal to integral x dp for all G. Because nu G is exactly x dp. Huh? But now my y is G measurable. My x was not G measurable. X had much more information. But I come up through this Radon-Nikodym theorem. I come up with this y, which is G measurable, but integrates like x on all the sets in G.
Okay, so here's the question I have. What is stopping y equals to x to be always true? He just said y to be x.
Well, y is
Sure
not.
that it's not G measurable.
No, x is not G measurable.
That's the only
issue. Yeah. Is this kind of clear to everybody? This is a very important point.
It's a subject one.
Yeah.
Then, okay.
It's a subsigma. So why would x be measurable set to subsigma algebra? See, that's the point. X needs certain amount of sets in your sigma algebra to be measurable. X lying in Borel's set, the pre-image of that should be in my sigma algebra. Omega says that X lies in some Borel set. So for X to be measurable, I need certain amount of sets to be present in my sigma algebra. G is a smaller sigma algebra. So X is not measurable with respect to G. But is there a proxy of X which is measurable? Yeah, that's what we are looking for here. Okay. All right. Yeah, so this is conditional expectation is not going to be easy.
So all we're saying is P is absolutely before was the term?
So nu is absolutely continuous with respect to P. Yeah. So whenever I have this property that nu G greater than 0 implies PG is greater than 0, which follows from this definition, that implies that nu has a representation integral f.
Okay, that's what the Rn theorem is telling us to do.
That's right.
There's a representation.
So Rn theorem is giving us this y. This y is G measurable.
And we just call that, denote that expectation of x given.
That's right.
Subscript.
That's right. Yeah. Well, yes, it's not a subscript, but yeah, we need a more graceful way of saying this thing, but this is fine. X given calligraphic G. That's what I've settled down to after years of saying this.
This is it hard to prove Rn?
Rn meaning?
Radon-Nikodym. Was it a hard?
It's demanding if you just assume that if your X is in so what's the
No, because all that we did, the existence is really hidden there. That's our one.
Yeah, no, I understand. I'm just trying to remember now. Right. So when does it become easy? Right.
No, so if that's the question, that means it's already hard.
Yeah, I mean, essentially, if I assume that my F is in L1, then it's hard. If I assume my F is in L2, then it's easy. So yeah, but I just want to make sure I'm not saying something wrong. F.
F the function.
Yeah, yeah. So I think, yeah, I just need to brush up to the
So
statement.
that we need mu and
Hmm?
you can't assume F is in L1 or L2 because that's a consequence. So what do you do with the premise?
Yeah, that's what I'm trying to exactly recollect. So yeah, I don't.
But you're saying in general it's not easy.
Yeah, under certain conditions it's hard. In certain general conditions hard. It's somewhat easier conditions. It's easy. Uh, it just slips my mind right now what that condition is.
Okay, so
But let me just tell you this slide. This should be fun. Yeah, go ahead.
I just have two questions. So we assume X is positive in the proof. I'm not being able to see why the same trick that we uses setting X into if X is not positive.
Yeah.
That's the usual trick of taking X.
That's
plus,
right.
but it
That's
works.
right. Yeah. So for x plus, you'll define E of x plus given G. For x minus, you'll define E of x minus given G. And for general x, it'll just be difference of these two.
Okay.
That will do the job.
So
Yeah.
conditional expectation is also linear there.
Yeah. Yeah. That's right. So we'll prove that later. True.
Yeah, and secondly, I wanted to ask, basically, I've forgotten, the time. Maybe we can.
Yeah, sure. You can come back to it. But let me just give you one more view of existence of conditional expectation. So again, what is conditional expectation? It's a random variable which integrates like x on the sets of a smaller sigma algebra G. And conditional expectation is with respect to smaller sigma algebra G, right? But the way to think about this is now your space. Just to have a geometric view, this is your space of all the random variables, L2, mu, F, P. L2 space of random variables. All the random variables whose second moment is finite. Okay? And they're F measurable. That's what this space means. So think of each point here as representing some random variable of that sort. What you can show actually, which we are not going to do in this class, is that this space is complete. Okay? Complete means that every Cauchy sequence converges to a point in that
I
space.
mean, we know that L2 spaces when it's not very just normal L2 spaces without measures.
It should be the same argument between
Same
both.
argument, but just get absolute almost not.
Yeah.
So each limit has an almost vertical convergence.
I mean, convergence in the L2 sense, right? That's a very well-defined notion. Yeah.
Then that's.
Yeah. But it also converges in probabilities.
That's actually the case.
Yeah, that's the same thing. So this, you understand this whole space is all the random variables which are in the L2 mu FP space. This is a subspace, all the random variables which have the second moment and are belong to mu GP space. So certainly if you belong to mu FP space, if you belong to mu GP space, you also belong to mu FP space. Hmm? In the Radon-Nikodym derivative? Yeah.
That's only the case for L1.
That's right. So now I'm assuming that my X belongs to L2 space.
It will be in L2.
No, so that's right. So you're right that right now earlier my random variable X only had to be in L1 space. Now I'm restricting it to be in L2 space to make this argument. I mean, I'm just talking about limited random variables. I'm not talking about random variables which belong to L1 but not in L2. But if they belong to L2, then I'm saying, okay, then I can define conditional expectation uniquely. And I can give it a geometric interpretation. So that's where I'm going with this right now. Right? But if a random variable is G measurable, then it's also F measurable. That's clear? Because F is bigger. Okay. So this is a subspace. Okay. It contains all the random variables, but it's so now imagine there being a projection y on the subspace of X. So that's the conditional expectation of X given G. Okay, that's the other way to think about this. I just have a geometric picture of all the random variables. You have subspace. Why is that the case? Because, so this is a subspace of this guy here. Y is a projection of X on the subspace. So Y is minimizing expected value of X minus W square for all W in G, right? I'm looking at all W in the subspace and find the closest point to X. Okay. That point will satisfy the property that X minus Y will be perpendicular to Z for every Z in G.
But is it always that in L2 spaces you take a subs, like L2 में projection? No, in L2, is it always true that consider L2 of F, script F, and if G is a subsequence algebra of F, then L2 of G is a subspace of L2
Yeah,
of F.
yeah. Because every G measurable function is also F measurable.
Oh, subs. Oh, yeah, and then
Yeah,
space.
second moment is finite, so where it's
No, I think you're asking.
when that, I mean, G is equal to F, then it's not strict.
You're asking
If-
space or- That is exactly.
But in the L2 space, you can define the idea of perpendicularity, right? You have the inner product notion. So yeah, all those Hilbert space ideas become relevant here. And then you conclude it's a complete space with an inner product. So it's a Hilbert space basically. And then, you'll have this property that the Y, which is actually a projection, is perpendicular, X minus Y is perpendicular to all the Z for all Z in G. So that means, in particular, I can take Z to be just indicators of events small g, right? And that this property here immediately gives me that E of X ig is equal to E of Y ig for all G in calligraphic G.
Professor,
Yeah.
doing a stupid question, I'm not understanding what it means to say. But what does it mean to say expectation of X minus W, where X is a random variable and W is a like set in a sigma algebra?
W is a
Belongs to the script G.
no, W is also a random variable. Oh yeah, no, so that's true. It's that's my mistake. This is a typo.
So belongs from L3 L2.
It should be M of G. It belongs to measurable functions in G. But really what I should say is, yeah, exactly. What I should say is in L2 of mu G P. I've told you in the class long time ago that I deliberately put mistakes here. I put many more mistakes here which I didn't know and you didn't know, so we just went through them, but some you caught.
That's why the second question I had was, so we know the L2 space is a norm, the two norm, which is this expectation of X minus W. Okay. So when you say expectation of X minus Y, Z equals 0, is that the inner product of this?
That's right. That's how you define the inner product, right? It's just expectation of X times Y. Okay. And now from here, this follows, right? I've just specialized these to be indicator functions. Okay. So this Y is indeed, it's G measurable and it integrates like X on the sets G. Yeah. Calligraphic G measurable integrates like real G.
So it's not just one more question.
Yeah.
And this is, the projection is specifically the orthogonal projection onto the subspace,
Yeah.
not any other kind of.
With orthogonal, it's well-defined idea, right? Yeah. So it's a Hilbert space.
And why is it that all indicators agreeing will imply the bottom line?
Well, what is this? So yeah, that's important
Then you
to.
think of this as test functions and approximation.
No, this is just another way of writing. So this is. No, it's good to say this. Because of space, I've not said this here, but it's X dp over G is equal to Y dp over
This is
G.
exactly that.
This is exactly that. Yeah. And Y is G measurable, so Y is equal to E of X given G. Okay. So not only are there mistakes, there are also gaps for you to fill in the notes. Lots of gaps. All right, so shall we carry on? Yeah, no, I'll just say a few things. Because I don't want to have Dhruman go away and not see this property here. So expect E of x given G is a random variable now. It's a bona fide respectable random variable, right? And it has an expectation. So expected value of E of xg is equal to expected value of x. Can you see why that's the case? So what's the
let's
expectation?
consider two cases. Case one, x is G measurable. Then this is easily true.
Okay.
And it's not at first.
Chalo, but this is what we are trying to find, right? This is what expectation means of a random variable. And we know it's exactly equal to this quantity right here. Because E of x given G
Oh, yeah.
integrates like x on all sets G in the sigma algebra calligraphic G.
But that's given.
Calligraphic G contains the whole space. So over the whole space also it integrates like x.
Calligraphic G doesn't contain the whole space.
No. So calligraphic G is a sigma algebra. Sigma algebra has to contain the whole space.
But
It's a smaller sigma algebra than F. So yeah, it doesn't contain F, of course, yeah.
so no, but G is the smallest sigma algebra of sigma.
Of the omega. I mean, let's just get this clear. So there's a underlying space omega. It is a collection of subsets.
I read that omega. Sorry,
Right?
I was thinking of that as sigma.
Yeah, no, that's what I thought.
Yes.
ठीक है.
Right.
So G is also a sigma algebra on omega, big omega. So it contains a set of omega.
So G is just a smaller sigma algebra than F.
That's right.
That's
Yeah, that's right.
Okay.
I mean, the way to maybe think about this is that, your F, for example, could be sigma of, let's say, Y and Z, and your G can be sigma of Y.
Yeah.
So F has more information than.
But for earlier we showed this is only true when x is G measurable, right?
No, X was never G measurable. E of X given G was G measurable.
Oh,
Yeah, X is F measurable. If X was G measurable, then there's nothing to talk about. So the point really is X is some random variable. We are coming up with a smoother version of it on a smaller sigma algebra. That's what conditional expectation does, right? E of Y given X. It's a proxy for X, right? It goes in the meetings and represents X. Okay? So it has this nice property that it at least integrates like X over all subsets in the sigma algebra Y. So that idea is what we're playing with, basically.
Sir, just to be clear, how exactly was this smaller sigma algebra constructed?
I mean, right now I've just said key, it's given to you.
And we can
And now, but one way to think about this is, your F can be sigma algebra corresponding to some variables, that's a sigma X, Y, Z, and your G can be just sigma of Y. So it's a smaller sigma algebra, right? Because F meant under F, all X, Y, Z are measurable. But under G, this is G. Only Y is measurable. So you need fewer number of sets. This is a nice way to think about it. All right. How much can I push you guys to stay here? ठीक है.
Is that reason why you're smooth?
What's that?
Why are you using the word? What do you
I mean, conditional expectations are kind of smoother versions, right? Because they are taking an expectation, right? So they're kind of averaging out with respect to conditional probabilities. Yeah.
that
So think of,
averaging?
so think of your, landscape here, and you've broken it down into subsets F, very refined. And F is defined, random variable X is defined, it's a hilly pattern defined on this smoother space. And now G is a more coarser space, fewer sets, and E of X given G is constant on sets G. So it's kind of a smoother version of it. It's a bad imagery. One can make it nicer, but I need to have to do some work for it. But you can think about this on your own time. It's worth thinking about in discrete setting, or why this comes up. So. Okay, so let's stop here. We'll do some more properties. I'm just worried that we won't be able to cover all that I am hoping that we'll cover, but it's all right, we'll manage. Maybe we'll take a few extra classes towards the end. Okay. Uh,
How of speed are we at, you think?
huh?
How?
Maybe,
Your plan.
Abhi, no, just maybe I think it's, yeah, I should check my plan again. But I think we are okay. Maybe a lecture, half a lecture behind or something. Yeah.
That's it. You are not
That's-
first class.
That's right. I mean, we'll probably cover less of finance. We'll cover the basics of it, but we won't do some funky finance stuff. But I think from your point of view, it's all right. You learn a lot of probability. What's that?
Maybe this person is not stochastic, calculus and mathematical financial, it's stochastic.
Okay, that's right. So you learn all of that, and that's worthwhile by itself. All right, everybody. I'll see you guys. Is there a chat here? Go on, go invited. Five guys. Okay, that's fine.
You can.
Okay, guys. I'll see you all